First presenter, Don Grant, National Applications Manager with Harvey Performance Company.
Well, good morning, everybody. Thanks for joining us, and thanks for having us. Productivity, I appreciate that. As Hope said, my name is Don Grant. I'm the National Application Engineer for the Harvey Performance Company. So just a little background on myself, real quick. So I got 32 years experience in the cutting tool industry. I had my own company for a long time, broke a lot of end mills, learned how to use a lot of end mills. So I appreciate everybody joining us on this webinar. Hopefully we can share some experience on boosting shop productivity by applying high efficiency milling techniques. Just a real quick background on us. We are the Harvey Performance Company, which includes Harvey Tool, Helical Solutions, and Micro 100, all based right here in the U.S. So we're pretty proud about that, and looking forward to actually running through this seminar with you guys. So first of all, let's just talk about the objectives, right? What are we going to talk about? I mean, this is a big button for a lot of people, high efficiency machining. So we're going to understand the top 5 current milling challenges. We'll kind of break that down because that's what we need to break down before we can actually figure out how to use high efficiency machining efficiently. We'll talk about what is high efficiency milling. What is it? Let's dive into it. Let's find out exactly what high efficiency machining is. And then let's understand chip thinning, TEA, which is tool engagement angle, and MRR, material removal rate. So all 3 things that really have a lot to do with running high efficiently. And if you know how to understand those, then you're going to really be able to kind of dive in a little bit more and understand what's going on at your spindle. So first thing, current milling challenges. What's the biggest milling challenge? Well, I can tell you right now, when we're talking about high efficiency machining, the biggest milling challenge we actually have is traditional tool paths. Now, traditional tool paths really conducive to what material we're cutting, right? We can talk about material until we turn red in the face, but there are a very great amount of material grades and everything else. So it all applies a little bit differently, but this isn't a 10,000 foot overview. So traditional tool paths, if you look at the picture I actually have here, is more of an offsetting tool path, right? So basically we're taking the end mill and we're offsetting it, kind of like a parallel offset. And we're actually creating all these conditions that the end mill doesn't like. We're trying to put the end mill in a really good situation with an HEM tool path. So in a traditional tool path, we have all these red areas in here where we start losing the corners, we start breaking end mills, we get all this chatter, we get bad finish, we get this chirping. So let's kind of break down this tool path a little bit, just so I can explain what's happening in a traditional tool path. So if we take a look at this, and this is a pocket mill, right? Pocket mill, we think, hey, we're just cutting a pocket. It's traditional tool path. We have an offsetting, but we're pretty much putting the end mill in a good situation. Well, after you ramp down or drill a hole, the first move that an end mill is going to make in a traditional tool path is what? It's a full slot. So that end mill already, first path it's going to make in a traditional tool path is going to be a full slot. So we're already, if anybody out there is machined with an end mill, knows that a full slot is going to create a bad situation. So after we clear out a little bit of that and we actually make another pass, we're actually doing a parallel offset, and look at what happens again. We're engaging the end mill again in more of 180 degrees of a radius. So again, full slot condition. So as we're running to the corner, things are looking good. This is kind of where we all program things, right? In a traditional like this, it's a peripheral cut. I'm stepping over 40%. Here's my speeds and feeds. Not when you're getting into that corner. You start getting into that corner again, where we're going to make another move. We're actually in a full slot condition again. Even if we come from the outside of the part in a traditional tool path, what's the first path we're taking? It's a full slot condition. So the right way to program any kind of traditional slot or a traditional pocket is by what? Worst case scenario. So this whole tool path that I just showed you should be programmed with worst case scenario, which means if you want the best life out of the end mill and you want that end mill to be predictable and work well, you have to program this for a full slotting condition. which is going to reduce our speeds and feeds. It's going to reduce how much axial we can take. It's going to reduce how many flutes we can take. And we're going to have a lot of scenarios and a lot of conditions that are going to put the end mill in a bad situation. Now, we're leading up here. This is like a story. So high efficiency milling, what we're trying to do is we're trying to take all the conditions out that make that end mill struggle and make it smooth. So the last thing and the last problem you have is going to be the end mill. We don't want you to worry about the end mill. So milling challenges, again, machine tools, old processing speed, older machine tools, limited processing speed, limited look ahead ability to actually read the code. A good example of that is maybe a traditional toolpath, if there's any G&M coders out there, might be 500, 600 lines of code at 12 inches a minute. Well, when we do an HEM or a high efficiency toolpath, that now just went to 10,000, 20, 30,000 lines of code, depending if you're putting a micro lift in there, and you're now running at 150, 200 inches a minute. So the processing speed on that machine has a lot to do with it. Lower rigidity, lower horsepower spindles. These also help, but are not limited. I want to let everybody know there.
She's so dumb.
Can you run on a lower spindle machine? Can you run these type of tools on there? Yeah, absolutely. You absolutely can. But it's really important to be mindful of what you're starting out with a machine tool. Let's take a look at another challenge, part fixturing, right? Part fixturing is a big one, especially as your materials get more heat resistant and harder and stronger. We have rigidity issues with this, right? We have part movement, depending on how you're holding it. Support is a big one, right? Anytime your tool or your material is hanging over the support mechanism, it becomes like a diving board. And the diving board, the further you get out, the more it's going to spring up and down, the more it's going to be detrimental to your tool life. So it's important to be mindful of these things. Clearance. How big are the toe clamps that are over the top of that part? How much are they hanging down? How much do I got to pull out that end mill? Clearance is a big one. Location. I love to bring up location when it comes to horizontal. I've walked into shops and I see where the vise is on a horizontal tombstone, and they'll have the vise all the way at the top of the tombstone, but nothing on the bottom. Be mindful that if you can bring all that down, that center of gravity, the rigidity, all the way down on the fixturing, you're going to have a greater chance at success. Stock to hold. What does your stock look like? If we're running a casting, you might run into a fixture that looks a little bit like this, but you have to be mindful on support, rigidity, and everything to make sure that your part's not going to move, because that's where you're going to get your chatter, and that's where you're going to get all your chipping, vibration, and tool deterioration. Tool holder accuracy, right? What's our holder look like? It's very important. The part that holds, that connects the tool to the machine, is the holder. It's important to get a really good holder. Old technology holders, side lock. People will still use side lock. Push that end mill to one side, you get TIR, you get indicator issues, you get vibration in there. It's important to make sure that your holder has good taper condition. Pull stud is in good condition. I've seen a lot of people where they're not mindful of the pull stud. It's important to make sure the pull stud matches the machine and is in good condition and tight. Excessive runout. We're looking for 5/10 or less is what we're looking for. You should demand 2/10 out of your holder all day long. That is not, something you shouldn't ask for. And unbalanced holders. It's important to make sure the holder that connects the tool is very important. Underutilized tooling. So now we can start getting into the tooling. If you're running a traditional tool path, we already know right away with that tool that you're using, it's going to be underutilized, which means we're going to run a conservative speed and feed. We're going to run a smaller axial depth of cut with long lengths of cut. This is where we're just dropping down with 15, 20, 100 thou with that end mill, even though we have a length of cut that might be 1.25 inches, 1.5 inches. I always say it's like going to Subway and buying a 12-inch sub and only eating 4 inches of it and throwing the rest in the garbage with no intentions of eating the rest of the sub. Buy the length of cut that you need for your situation and that end mill. Now, if you're running a prototype, it's a little bit different. So I'm not standing here slamming my fist down saying you have to use that type of tool. But if you're running a production environment, it's very important to use the length of cut on the end mill that's going to be conducive to your program. No corner radius. Put a corner radius on there. It's underutilized tooling. You get poor tool life, unpredictable failure. We're trying to get predictable failure. We want it to be predictable. Deflection. We get a lot of deflection by taking light axial depths of cut and heavy radial depths of cut, which is going to bring in your chatter, and it's going to give you low MRR that we're going to actually talk about. So now let's just dive into what is high efficiency milling. What is this? We like to say the 3 T's of HEM over at Harvey Performance. You have the tool path, you have the tooling, and you have the technique. Those are the 3 things. Number 1, tool path. Tool path employs intelligent toolpaths generated by CAM, so CAM software, that strategically manages cutting forces and maximizes productivity. Here's the beauty with HEM, right? You don't really have to do much with the G&M coding. The toolpath, the CAM software is actually going to do that for you. Tooling utilizes smaller end mills. Now we're going with smaller end mills, higher number of flutes. We can add flutes, so we have a heavier, stronger core, and we can run at elevated, higher speeds and feeds. We can push this tool faster, so our MRR, material removal rate, is going to get better. Our cycle times are going to be reduced, and we're going to get better tool life. And then the technique, which kind of pulls it all together, we're going to employ light radial depths of cut, which means your step over on your peripheral is going to be light. We're going to go higher axial. So remember that length of cut, that subway, we're going to eat the whole 12-inch sub. We're going to use the whole length of cut, depending on what our program looks like. We're going to employ chip thinning, which is something we're going to talk about. We're going to control the angle of engagement, which means if we control the angle of engagement, we can control how big the chips are, and we can control how many flutes, and we can make an end mill that's a lot stronger. So those are the 3 T's. Intelligent tool path. Now you can take a look at this strategy here. And this strategy now, instead of slamming into corners, we're actually picking out the corners. This is a dynamic toolpath from Mastercam. This is something that is within the CAM software that's going to manage the forces on your end mill. That's what we want to do. We want to manage the forces with HEM on your end mill. Dynamic toolpath is going to do that. And you can see in this where it's actually picking out the corners and making sure that end mill is in a good condition. So now that we're taking light radial depths of cut, we're taking heavy axial depths of cut, instead of using the 2, 3, 4 flute end mills, we can start going up to 5, 7, 8, 12, 16. You can really start managing your end mill with your flute count to put it in for your material, your radial step over, your core strength, your rigidity, and everything else. So now that we can get a tool path that's managed and a strategy for HEM, we can really start utilizing the tool and making sure we're using it to its fullest potential. So if you look at this slide, on the left, you can see we're having 2 things that are going to kill an end mill right here. Heat and vibration. We're trying to take the heat out by employing a lighter radial depth of cut, because when we take a heavy radial depth of cut, we put a lot of heat in the end mill. But because we put a lot of heat in the end mill on the left-hand side, we have to limit our axial depth of cut. When we limit the axial depth of cut, we bring a lot of vibration in. Because we're taking a heavy radial, we have to limit the number of flutes. And this is where we kind of get 1 flute in cut, 1 flute out of cut, 1 flute in cut. So you don't get a stabilization of the end mill, okay? And this is what brings vibration. It's kind of a slapping effect. 1 flute in, 1 flute out, 1 flute in, 1 flute out. And we get a lot of chatter and chipping that way. By going to the actual condition HEM on the right, we can stabilize the cutter. We put more than 1 tooth in the cut, okay? That's number 1. That's where the vibration stabilizes this. And end mill, believe it or not, is under load when it gets in the material. If we put it under load and take it out, you get that deflection as you get on the left. But what we're trying to do is keep it under load. HEM tool paths, such as dynamic milling, will actually control the load on the end mill and stabilize it. Because we're taking a light radial depth of cut, we take the heat out. Now we get rid of the heat. Heat's going to deteriorate the end mill, so now let's get rid of the heat by actually employing a lighter radial depth of cut, which means the flute is in the cut for less time. Now, this is very important to understand because this is a 10,000-foot view. Trust me, anybody wants to call me on this side, I can dive into it. But This is very important to understand with this diagram right here, that it is very conducive to the material you are cutting. All material dissipates heat and pushes heat back into the cutting edge differently. So if I was running Inconel, my radial step over would be a lot less because it's pushing a lot more heat. So if you look at the radial step over on the left, you can see the heat zone is very small. And so we get this cool down period. And especially if you're running coolant, you're in the coolant longer. So we're not putting as much heat into the cutting edge. As we actually step over that radial more and more, that heat starts getting in the cutting edge. So this is a great slide. And this is a great way to understand if you're cutting Inconels, Hastelloys, Manels, Nitronics, 13/8. Take a look at your radial step over and see if you can't back off that radial step over to reduce some of the heat, depending on what your end mill looks like, and you will start getting better tool life. Now, it's not just the radial step over. Understand that. We're going to dive into it a little bit more, but it's not just the radial step over. There's a combination. Chip thinning. Dangerous word, chip thinning. Chip thinning is basically when you take an end mill and you step over less than 50% of the diameter. So a good example of that is half-inch tool. If I'm stepping over that tool less than 250 thousandths, it causes the chip to be formed to be less than what you programmed. So if you program a tooth thou chip inch per tooth, and you are at a 10% step over, that tooth thou inch per tooth you program, that chip becomes a lot smaller and a lot thinner. And trust me when I tell you, as a engineer, as a end mill company, we recommend a chip thickness to get underneath the material and accommodate the rake on the tool. So if you're not actually taking the chip, you're going to deteriorate the cutting edge and you're going to have problems. So it's very important to maximize the chip. So when the chip gets thinner, how do we get it thicker? Well, we speed it up. We run faster. Well, faster is good. Faster means that I can get more cycle time. So now that we're employing a light radial and we're taking a heavy axial, we can also start running faster because we have chip thinning. Tool engagement angle also has a lot to do with it, TEA. So as we start reducing the radial step over, our angle of engagement on the material becomes smaller. Look at the one on the left, 50% of the diameter, the angle of engagement is 90 degrees. As we go all the way to the right, that angle of engagement gets smaller. So why is this important to have a smaller angle of engagement? Well, number one, it's important because the chip is smaller. And if the chip is smaller, I can put more flutes. And if I can put more flutes, I can run faster. And if I can put more flutes, I get a bigger core. And if I get a bigger core, I get more rigidity. And it just keeps going and going and going. So by controlling the angle of engagement, we can actually control the forces on the end mill. Now, the strategy, Mastercam dynamic milling, does this for you. But you want to be mindful of what that radial step over is recommended for that flute count for what you're actually doing. So that angle of engagement is really being controlled. Because in a traditional tool path, if you take a look at this, when you go into a corner, angle of engagement changes. That's where we get the squealing, right? We run an end mill, goes in the corner, squeals, get chatter. Then we start running along the straight line, angle of engagement is manageable. Believe it or not, when it goes to the outside, angle of engagement gets smaller, chip gets thinner. So we're not managing the forces in a traditional tool path. We want to do that. So here's a great example of TEA and the cornering. We run a tool into a corner. Remember how we get squealing traditional? This is what's happening, folks. This is exactly what's happening. You're taking that tool, you're running into a corner, your angle of engagement is 30 degrees. You get in the corner, you're greater than 90 degrees. The chips have nowhere to go. You start getting squealing. Better desired situation is maybe pick out the corners, but you're still doing it at a 90-degree offset. Your angle of engagement is still great. I'm telling you, HEM, let's go with a smaller tool. Let's reduce the carbide cost. Let's reduce the cost of the carbide. Let's pick out the corners with a higher axial, lighter radial, and let's control the angle of engagement, and let's get the tool life on there. That's what we're shooting for. That's what HEM does. It manages the forces in those corners. Metal removal rate, or MRR, great calculation. This is how we kind of get judged on efficiency when we're actually programming something. How many cubic inches of material am I removing a minute, right? So there's three things to factor here. There's a radial depth of cut, an axial depth of cut, and an inch per minute, or a feed, right? So this is how you calculate inches per minute or cubic inches of material removed. It's your radial depth of cut times your axial depth of cut times your inches per minute. Take all three of those, multiply them. That's how many cubic inches of material you're removing per minute. Now, I love this slide, and I know we're a little bit limited on time, and I don't want to take up a lot of time. We're just about wrapping up here, but these three things are very critical to the success of your end mill. You have three things to play with. Keep in mind that you have a radial depth of cut, you have an axial depth of cut, and you have an inch per minute. I call this the MRR triangle. You can play with any three of these things to maintain your MRR, but keep your end mill in a great situation. Example, my radial depth of cut is too great. It's choking out my end mill, reduced my radial depth of cut. My end mill likes it. It can manage the chips. Increase your inch per minute because we have more chip thinning. I can run faster. My MRR is maintained and my end mill is in a good place. Very important to look at all three of these things. And before you start throwing end mills out and getting a different one and trying something different, take a look at all three of these. If you look at MRR just based on radials and axials, I'm just going to focus on the one on the left and the one on the right. 2 times D on the end mill, but only a 4% step over gets us 4.83 cubic inches of material removed per minute. If we just go traditionally on the bottom, quarter times D, but 40% radial. So now we're hogging. The machine sounds good. Sounds like we're removing a lot of material. Guess what? 0.488 cubic inches of material. Which one are you going to choose? Choose the one with the highest MRR, and it's going to be more conducive to your tool life, and it's really going to save on your machine tools and everything else. Key questions to ask. This is what we're going to wrap up with. Is your tool holding optimal? Is that fixturing good? Are you in a good place? Does that look like it's in a good condition? Are your part holding conditions ideal? Is your spindle condition in good shape? How many times did you crash it this week, right? I've been there, trust me. That's why I say that. Does your shop culture fit this new methodology? This is a learning curve if you're not doing it. So it's something you kind of want to embrace this change. Are you willing to look at reducing your tool diameters? Of course, who doesn't, right? And now that diameter is conducive to how deep you're going. Just be mindful of that. We can help with that too as well. Do you have the CAM package that will support HEM techniques? Mastercam, dynamic milling, go for it all day long. That'll take care of it. Do you know your material exactly? What are the certs to hardness condition? It's very important to understand this to change those parameters. And are you roughing enough material? If you're doing a prototype, might not be as important as if you're doing production run. So with that, I appreciate your time. I'm going to hand it back to Hope, and thank you.
Thank you very much, Don.
Hello, everybody, and thanks for attending this webinar. My name is Patrick Philippek. I am a support technician for Mastercam up here in Minnesota, working for Prototech Engineering. Prototech is located in Chaska, Minnesota. We are the local Mastercam dealer, and we are American-made CAD CAM software. So after this, if you have any questions about what I talked about or with Mastercam, definitely give us a call, and we should be able to answer any questions you have. So today we're going to talk about efficient roughing and finishing processes. First of all, we'll talk about dynamic roughing. Second, we'll talk about dynamic rest roughing. And then third, advanced multi-axis finishing, barrel and taper form cutting tool strategies. Number 3, I think, is the next biggest thing in manufacturing coming up. So we'll discuss all these topics. So dynamic roughing. Why is radial chip thinning important? Don related to that a little bit, and we're going to see in Mastercam how we take care of that. What is dynamic roughing, and why should we use dynamic roughing? So why is radial chip thinning important? As the step over gets smaller, the chip becomes thinner, obviously, and we must increase the feed rate to maintain the chip load. Mastercam will do this automatically for you in dynamic toolpaths. So there's not a whole lot you have to do. Just got to plug in the correct numbers, and Mastercam will take care of the rest for you. So the results of radial chip thinning, as we can see here, a smaller step over allows us to use a much larger depth of cut. This results in a much higher material removal rate. Obviously, if we can use the whole end mill and cut to full depth with lighter step overs, you're going to increase your cycle time, or decrease your cycle time, I should say, dramatically, other than the traditional tool paths of a small step over. This is easily applied to straight cuts. What about the more intricate shapes, complex pockets, radial features, stuff like that? Well, the answer here is dynamic roughing. dynamic roughing and Mastercam takes care of pretty much every scenario you need, utilizing the radial chip thinning. So we're never going to over-engage, we're never going to under-engage our tools in these tool paths. So what is dynamic roughing? Mastercam's dynamic roughing applies to the principles of radial chip thinning to all parts, regardless of size and shape. This works for everything. It doesn't really matter what you're cutting. These tool paths can apply to that. All tool paths are 64-bit, multi-threaded, and multi-cored. What that means is it's going to process faster when you're programming. We have 2D roughing and rest roughing, and 3D roughing and rest roughing that we'll talk about. Dynamic roughing continuously adjusts the tool's trajectory to maintain a constant chip load. Dynamic roughing uses a constant feed rate, and dynamic motion is not a feed rate optimizer. So I want to discuss this a little bit. We use a constant feed rate. So you get this from your Harvey Tools manufacturer. They'll give you your feed rates that you're supposed to be running. Mastercam outputs that feed rate and does not change the feed rate. We are not a feed rate optimizer. This changes, or this is the difference between some of our competitors. We don't slow down and speed up our feed rates in our program. We apply different step overs if we are in a situation where our chip is thinning out or getting heavy, as you can see in that picture there. And the corner, obviously the chip load is going to be lighter, takes a little bit heavier cut to maintain chip load. That's what this is all about. In the next video here, it's going to be dynamic motion versus traditional motion with a little time study on it. So as you can see, the left one there is full depth, radial chip thinning, dynamic motion. The right one on the right there is more of your traditional motion, smaller step downs, heavier step overs. And as this process is through, the one on the left is finished at 1 minute 57 seconds. And the one on the right is still chugging away. And it finally finishes out at about 3 minutes 37 seconds, so quite a bit of difference there. And this is what we typically see right over the board, usually a 60 to 80% cycle time reduction when we do get people to switch over and try this strategy. Why use dynamic roughing? Tool is always in the optimum cutting condition. Along with faster cycle times, we're also seeing tooling last 10, 20, 30, 40 times of what it typically would with traditional tool paths. Very important. Faster run times. With these tool paths, now we're seeing feed rates 2, 3, 4, 500 inches a minute. Not out of the question here. So obviously your faster run times are going to come from a lot faster feed rates. Longer tool life, kind of what I was talking before. If we're in our optimum cutting conditions, our tools are running where they are supposed to be running for chip load, they should last longer. Reduced programming time. Dynamic tool paths are easy to program. Mastercam takes care of our tool path for us and takes care of the step overs and everything else so we don't over-engage our tool path. Easy on the machines. Something that in my mind kills machines is when you go into a corner and it chirps at you. With these tool paths, it's impossible to go and T-bone into a wall or go into a corner straight in and take a left. So it should be a lot easier on your machine to not overload your spindle constantly. Heat is carried away by the chip. Parts are cooler. When we do these cuts, we typically try to cut them dry. Right after we're done with the cut, you could typically go and grab that part and they're lukewarm from when we put them in because all the heat is carried out with the chip. Easy, consistent, and repeatable. So you can take a lot of different scenarios, a lot of different parts, and you're going to get the same results with every part, depending on your setups there. And all machines will benefit from dynamic roughing. So if you have a slower machine, a faster machine, they'll all benefit. There's no restrictions here. So that's kind of our dynamic roughing, a little bit into that, a few questions answered there. We're going to move into stock model and rest roughing next and why this is important. So we're going to talk about what is a stock model, what is rest roughing, and is this efficient? So What is a stock model and how can a person use a stock model? So a stock model is a Mastercam created .stl file. So pretty much it's building an STL file with the data that you give it through Mastercam on what you want to see. Stock model gives the rest roughing passes the actual cut data. So when we come back with a smaller tool, now we're going to take the data out of this STL file so it can calculate a cut from there. Stock model can be used on 3, 4, and 5 axis machines. Really no limitations here for machine. Visualize what is left over from your roughing op. So you can see what's going to happen, or in the machines when you open the doors, you should be able to get a visual effect on that. Elimination of air cuts. We're going to keep on coming back to elimination of air cuts. Something I see a lot in the industry is a lot of people cutting air. The stock model is used pretty much mainly to eliminate air cuts or bad cuts. So if we're going to do our HEM principles and go fast and be as efficient as we can, if we're cutting air down the road, it's really not going to do us much good at the end. So elimination of air cuts, huge. And here's a stock model. So we start with just a piece of stock. Our first op was going to look like this, and this is what Mastercam can create to reference from. Third picture is after first, second, and third op. Now we got some stock left over in the top center, and then our finished part here. So that's what we can create in Mastercam. So in process stock tracking. So you use Mastercam stock model to represent the stock shape like I showed you previous at any point in the process. Track the stock from index to index when doing 3+2 roughing. So if we have a machine that can index, now we can cut the first op, and if we index it over, now it's not going to apply air cuts where there's already material roughed out. And once again, track the stock across multiple setups. Maybe this would be a multi-vice setup where you're manually switching them parts out. And once again, we're going to eliminate air cuts as we go to the next op. So elimination of air cuts by processing off of a stock model. So here's a little video of kind of what I was talking about on that part. So we have that part up there, and we have a little bit of stock left over just on this one side. So instead of cutting a big chunk of material or referencing from that, it's going to reference right off the stock model where the material is left over and eliminate all of our air cuts for us. So in this case here, not cutting any air, not looking at the theoretical stock that we started with or referencing from that. And it's just going to apply cuts where there's a little bit of material left over on from the roughing op, previous roughing ops. So when to use rest roughing? So when should we do these strategies? Are you indexing your part in the machine? And these are questions you have to ask yourself and if it can be useful. Do you have more than 2 sides of your part that you are cutting? Do you cut complex parts with a lot of features, a lot of pockets, hole features, all sorts of stuff going on in there? Roughing cycle times, bigger tool, bigger step overs. So if we can use a bigger tool and come back and reference from what's left over, maybe we can save some time there. Minimize the work your smaller tools need to do in a corner. So, if you can come in there and just reference what's left over, so your smaller diameter tools can come in there and not break off. They know exactly what's left over in them corners. And once again, elimination of air cuts. Coming back to that again, but that's kind of the main deal here. We want to eliminate air cuts to be efficient. So indexing on a 4th or 5th axis machine. So after cutting the first side in this situation here, a stock model is created to reference from. In this case, it would have been a lathe op that we would create a STL file from. It'll look at the shape of the part. So the blue is actually an STL file. The next index and rough will take this information and use it to eliminate air cuts. So if we didn't do this, it may be looking at stock that is true round yet, not turned down, where now we can look at the blue on the screen and it will reference from there and only put cuts where the blue section is. Once again, elimination of air cuts. But what about like 2D pocket style features? We've been kind of looking at more of the 3D parts there. We can, by using a tool with a bigger radius, then the finish radius in the pocket. So this would be a case where you're taking a 1/2 inch end mill, maybe going in and pocketing out as much as you can, coming back with a 1/4 inch or a 3/16 to finish out the corner radiuses. Kind of the same thing here, using a small tool to achieve a radius in a corner, kind of the same situation there. And, you know, if you don't want to make a stock model, you don't have to in Mastercam with 2D pocket style features. We can utilize a stock option right in our Mastercam toolpaths to pick an operation to calculate from. Pretty much what that means is it'll look at a previous toolpath, see what material's left over, and then just put cuts where there is stock left over, you know, to eliminate any air cuts, you know, over engagement, anything like that. So our rest roughing really caters to the high efficiency machining, just in a smaller platform of saying what's left over, where should I apply my cut so I don't over engage or under engage my tools. So absolutely take a look at some rest roughing. It's huge elimination of air cuts and to optimize your smaller cutters. The last topic we'll discuss here is advanced finishing with circle segment cutters. In my opinion, this is going to be the next big thing. And this is for finish strategies. So typically a ball end mill, if you're traditional tool pathing, you have small step downs to achieve your surface finish. So we're going to answer some questions here with these advanced finishing circle segment cutters. And I want to go back here. So what are barrel and taper form cutters and why use them? Advanced finishing with 3-axis machines and advanced finishing with multi-axis machines. So what are advanced finishing cutters? They are small diameter tools that provide a large effective cutting radius. These tools vary depending on who's grinding them. Harvey is now grinding these tools. I've seen some that have anywhere from a 3/4 inch radius on the side to 3-4 inch radius on the side. So it really depends where you're buying your tools to get this information. The shapes they typically come in are barrel form, taper form, and lens form. And they're available in solid carbide and indexable. So take a look and, you know, go to your tooling vendors, Harvey Tools, and see what they have available, and then go from there. So why use advanced finishing cutters? 10, 20, 50, 100 times, etc. Smaller cusp height by using a large effective radius. What this is all about is the huge effective cutting radius on the tool to eliminate the scallop. So here's a little illustration I put together. A larger tool radius equals a small scallop. A small scallop equals better surface finish quality. And here's a comparison of kind of what we're talking about. If we're taking an 1/8 inch ball end mill and a 1/2 inch ball end mill and stepping over the same amount, you can see the scallop in between the cuts are obviously going to be a lot smaller. So why use advanced finishing cutters? A small cutter radius gives us access to tight areas. So in this situation here on this 5-axis part, we're taking a smaller ball end mill because we can fit in between the features there and get as close down to the floor as we can. A smaller cutter radius requires some small step overs. Obviously, we need to really minimize our step downs to be able to get a good finish. In that case, it may be a 5 thou step down and 8 thou step down to get our finish that we need. Now I was just talking, well, a bigger radius is going to give us a better finish at a bigger step over. So that is true. You know, larger step overs to attain a good finish. But in this case here, a larger cutting radius does not allow access to tight areas. So we run into a lot of them situations where we can't fit a big tool in between the features on the part. And we can't get close to the floors in this case either. So part shape here is going to dictate the cutter selection hugely. So in this case here, we had a small ball end mill. The limitation there was small step downs. Big ball end mill, if we put that in, now we can't fit in between these features. So circle segment cutters, what we're talking about here, a taper form tool, provides the best or the finished benefits of a large radius cutter while retaining the access of small cutters. So in this case here, in the same cut, now we can take a taper form with a large side radius on it, and we can be stepping down 30, 40, 50 thousandths to maintain the same scallop we would have had with a step down of maybe 5 thousandths, 10 thousandths. So it's huge. 3-axis machines, these are limited. I will say this, they're limited in 3-axis machines, okay? So we can still use barrel form, taper form for vertical and steep walls. You're probably, depending on the tool grind, you're probably not getting much over 10, 15 degree taper on a wall and be able to do it. So they are quite limited here. Lens form. Lens form looks like an end mill, but has a huge radius on the bottom of the tool. And these are for shallow floor features. Lens form can be used in the face or flat, free-flowing surfaces. So, you know, in this case here in this picture, we have a flat surface with maybe 1 degree of taper, and we have a little pocket in there. What looks like smooth flowing detail can still cause problems here. That pocket's going to create a lot of problems for us. As you see, the radius of the tool is contacting the part, leaving a very large cusp. So we'd be able to do the flat section. The pocket, we're going to still have to come back and do a different strategy with probably a ball end mill in that case. So they're not a fix-all, but for most situations, it's huge at time savings of what we can do here. Advanced finishing with multi-axis machines. So the left is just a basic ball end mill. And then the right picture here is going to show a multi-axis application where we're stepping up 50 thousandths to achieve the same finish on the part. So like I said, these are relatively narrow applications on 3-axis machines, but multi-axis machines allow these tools to be used almost everywhere with very few restrictions. So pretty much what I'm saying is you got a machine that has multi-axes in it where you can either cut while rotating or you can tilt or tip the part. Pretty much there's a lot of situations that you can do and not a lot of limitations there. Now, we do have to kind of be smart with this a little bit. Obviously, this is not a good application for this tool type. We're not cutting it like this. We'd be cutting it along. So you kind of got to change your programming around a little bit. Obviously, this is not going to work. And one thing with this is Mastercam's toolpaths support these tool shapes. That's very important to note. We've done a lot of testing to make sure that we can define the tools to drive off the tools correctly. We're one of the only ones that can do that by tool definition. So make sure if you have a CAM package out there that they can drive off these tool definitions correctly. Otherwise, you're going to have varied results there. So we're still in our multi-axis state here. So we can tilt this tool or tilt this machine every which direction we want. So like I said, critical to the success is the ability to control the angle of the tool relative to the model at all times. So in this case here, we went into a multi-axis cut, to either a morph or a parallel cut in this case, and we decided to tip the tilt angle to 78 degrees. That's going to make the tangency point near the tip of the tool, allowing the tool to finish close to the floor. So as you can see where the red is on the screen there, we're getting pretty close to the bottom of the tool with a 78-degree tilt angle. Ideally, we would want to cut near more towards the OD, so we have better surface feet a minute and better chip evacuation. We can simply do that by just changing the tilt angle to 85 degrees. And typically, you're going to be between 78 and 85 degrees, somewhere in there, depending on where you want to cut with these tools in the tool path. You know, the tangency point here is much higher. You're probably going to get a little bit better surface feet a minute out of that cut there. Here is cutting a blade with a ball end mill, small step downs. We have to step down to achieve our surface finish there, and it'll flip over to a taper form tool, where now we're stepping down maybe 40, 50 thousandths. So comparatively, 8,000 step down on the previous to now we're going 40,000 step down, maintaining the same finish qualities as the ball end mill, just that much quicker. So there's kind of the proof on what it can do. Huge step downs compared to small step downs. In this case here, the angle of the tool is changing as it works its way down the part. Great for spreading out the wear. Bad as the surface feet a minute is not consistent. So when we program these, we kind of got to look at our strategies here and look at our machine and what are we able to do with that machine. Like I said, if we can tilt the machine, now maybe we can come in here and tilt at a certain angle and then just drive that tool right down that face. So this would be a better situation instead of trying to tip the tool, just to drive it right down the face after tilting with planes and Mastercam. We can finish the walls from the bottom up. So here's a true 5-axis cut, the parts moving all over the place to maintain that 78 degrees or between 70 and 85 degree cut tilt angle. As you can see, the part moves all around. So if you have a machine that has the ability to cut while rotating, a true 5-axis machine, like I said, you can really do some pretty radical stuff with these tools. In this video here, I'll play, it's kind of a side-by-side comparison. The left picture is going to be a ball end mill. It took 12 minutes, 55 seconds. The one on the right is a taper form tool. It's going to be 2 minutes, 56 seconds to cut the same distance and get the same finish qualities on here. And that's going to result in a 77% total time savings. And that's what we're seeing over the board. You know, we're seeing some huge time savings for the people that are kind of going into this and trying it out. And, you know, large radius circle segueing tools allow for deeper step downs and fewer finish passes. So I definitely highly suggest trying these if you're doing a lot of surfacing. I think you'll be quite impressed with the performance of them and the time savings. We did test cuts here, productivity, on the Washion Vesta 1000. It's a very nice machine. If you guys are interested in looking at some new machines, this machine's a decent priced machine, and it handled these high efficiency milling cuts very, very well. I was quite impressed with the machine. So definitely take a look at one if you're looking at a new machine. We cut 4140 pre-hardened material. We use the helical 7-flute 1/2-inch end mill. We're going 8,500 RPM and 350 inches per minute. Around the outside, we're going 1 inch deep. The center pocket cut, it was 1 inch deep also, and we had a couple of 1 step up on there. And these were all programmed by Mastercam's dynamic toolpaths. I programmed the part in probably 15, 20 minutes inside of Mastercam 2021. So very useful. Very easy to program, and repeatability. So definitely take a look at Harvey Tools, helical tools, productivity for your machines, and take a look at Mastercam to see if we can help you guys out. So we did these test cuts, like I said, a couple weeks ago, and I want you to listen to the sound when you get into there. Let me share this. There we go. And once the sound kicks up, I want you to just listen to the sound. And if you can, take a look at the chip also. The chip is coming off nice as straw color and then moving to a blue cut. And one more note on this. When we get to the center bore, we had 2 end mills. We tried one without a chip breaker and one with. And the one with the chip breaker is well worth looking at in a situation like a pocket where you can't evacuate the chip. It was a huge difference when we got to that. Situation, especially for spindle load. You know, we're running a higher spindle load, and that cut it down by 20% just by going to the chip breaker. Let's go ahead and take a look at this. Next, it will be that center hole. So just look at chip evacuation. This is where the chip breaker helped immensely. Here's some rest roughing with a 3/16 tool to come and clean out the corners after we roughed. So any little corners that we couldn't reach with a 1/2 inch, we came back with a 3/16. Dynamic motion, once again, just rest roughing. And here's the advanced finishing. 40,000 step up to maintain the same scallop that a 3/8 ball end mill would have had with about a 10 to a 8 to a 10,000 step. And there's the finished part. All right, thanks, guys. I believe we'll take some questions now, and if, as always, if you guys have any questions after this, you can always email us in if it's a question you have down the road. Be happy to help you out.
Thank you, Patrick. We do have a couple of questions. Darren has asked, and this is for Don, is there a basic MRR for each diameter end mill that I can use and apply to know if I am getting close to removing optimal material?
Yeah, and hope that's a great question. We've been kind of going back and forth a little bit in the chat, but here's the thing with MRR. Like I said, MRR is based on radial, axial, and then feet or inch per minute. That's the calculation for MRR. So is there a basic MRR? No, because there's a lot of variables. But what there is there is recommendations based on the tool path and the tool for those three parameters: radial, axial, and feet per tooth. So by just knowing what the material is and what the tool path is, then we can calculate what that MRR should be based on how that tool should perform in that material. So yes, you can calculate that before you actually run your part if you know what your tool path is, and then you pick the right tool. It can be calculated by those three things, but there's not like a spreadsheet that says, you know, titanium should be running at 6 cubic inches per minute. It can, but it can also run at 3 efficiently depending on what your axial is or what your program is. There's a lot of variables. So I hope that answers the question, and we can easily figure that out for somebody.
Thank you. And Patrick, we had a question for you. Paul was asking which tool holder that was, and I replied back, and I hope I was correct on this. The 1/2 inch HEV7 Flute Helical Solutions 27287.
If he was asking about the holder, maybe Darren could chime in on that one. I know they were Regal fix holders, but I'm not sure which holder that was.
Okay.
Yeah, the Rego fix holders were all the PG25 Big Plus in that machine.
Thank you. And also, what do you go up for the micro lift?
Micro lift, all depends on what you want for a finish or a semi-finish from roughing. So in this case here, I believe we're stepping up 10 thousandths, or I'm sorry, 10% of tool diameter. So I think we're stepping up 50 thousandths on that when we rough that finish or rough that center pocket out. Highly dependent on your tools, how big the tools are. Smaller tools, usually the smaller the scallop you want. That's going to be kind of part specific, but typically when I'm doing a lot of programming and coming back, say with the ball and more or accelerating finishing, typically it's a 10% step up, max 5% depending on tool size.
Okay, thank you. I would like to thank you all for joining us today, and thank you to our presenters, Don Grant from Harvey Performance Company and Patrick Philippek from Prototech Engineering.